exam is Monday. We'll probably do let's do the quiz on maybe Thursday. Does that work? All right. So exam will be on Monday. We don't have class on Tuesday, so we'll do and Wednesday is the analysis, so that's going to take a while. I don't want to use extra time there, so we'll do the quiz on Thursday on chapter 10. Okay, so we've got all these molecular shapes. We know that stuff. What do we use them for? We can use these shapes in a couple ways, but one way that we can use them is to think about polarity. This is really important. Pretty much the entire next chapter, chapter 11, is going to be using this idea. So we've talked about bond polarity, if you remember. I hope you remember, because that's going to be on the exam. Right, you can have these covalent bonds like between C and O, where you have the electrons pulled more toward one side, and that makes partially negative side and a partially positive side. So we've done that. We didn't really talk about what happens when these things are in molecules. Right? So let's look back at what a molecule actually looks like. We can use our visualization tool here again. Oh, our activation code expires today. I hope they update it. All right, so let's just look at like a basic methane molecule here. Oops. All right, there's our methane molecule, tetrahedral. And this ball and stick representation, which is what that's called, is a really nice way of showing how things are connected and shapes and all that stuff. But if we want a better picture of what the molecule might actually look like, any ideas what that's called? Or what that looks like? Well, what do electron clouds look like if you put them all together?
Points.
Yeah, and they kind of overall make a sphere. So you've got different orbitals and stuff, but if you put it all together, you have basically a sphere. And we talked about what a covalent bond means. What's a covalent bond?
One metal paired together.
Yeah, but what does it mean that they're paired together? What is that saying?
Shared.
They're shared, and how are they shared? How can two atoms share electrons? Their valence shells have to be close enough to actually intertwine. So there has to be overlap between their shells, right? So in order to have that overlap, or what that actually ends up looking like, is this. This is called a space-filling model. So here's our methane molecule. But now what we see is the overlapping spheres of electron density, which is a better picture of what that molecule would actually look like. And depending on the sizes of the atoms, that could be a little bit different. So the reason we're talking about that now is that when we think about polarity in terms of an entire molecule, we can't just say like, okay, this one bond is polar, and so therefore it can attract other bonds in that same way. We have to think of the molecule as a whole, because the electrons are going to be over the whole molecule. When we get into molecular orbitals, we'll see that that's even more true. So to determine the polarity of molecules, if a molecule is polar or not, we have to add up the bond dipoles. And we can do this by thinking about them as vectors. and just adding them up. You can do this quantitatively if you have all the information to do that, but we would just do it qualitatively, kind of looking at it and seeing what happens. So let me show you what that looks like. Let's take a water molecule. Now, in order to do this, we need to know the shape of the molecule, because we'll get different answers if we use different shapes. So what's the shape of the water molecule? Yeah, bent. So we can draw the water molecule like this. And then we can look at the individual bond dipoles in the molecule and add them together. So each bond in OH is polar. Which direction are the electrons being pulled in the OH bond? Toward the oxygen or toward the hydrogen? Yeah. No, the opposite. Well, you're right, the hydrogens are more positive, but that means the electrons are being pulled toward the oxygen because electrons are negative. So electrons are being pulled more toward the oxygen, which means our positive side is over here and our negative side is over here in both cases. And we can draw those bond dipoles like this. So we can say that's the direction that the electrons are going, from the hydrogen to the oxygen. If we want to know the overall polarity of the water molecule, then we need to add those dipoles. How do you add vectors? I remember old physics classes long ago. What? Yeah, tip to tail or head to tail. So we want to line them up so that they're kind of taking a path. And the ultimate sum of that path is going to be the adding of our vectors. So we're going to take this vector here, the first one. Let's have a little more room here. So that's going to be our one vector from the left. And then the other vector, we line it up at the tail, tip to tail here. They're both the same size vectors. They should have the same magnitude. So our overall vector is going to be the bottom of one to the top of the other. Like that. So that means that the overall dipole in water looks like this. So we can talk about the individual bonds having different poles from the having a pole of the electrons being lopsided, however we're going to talk about that, having a negative and a positive side. But we can also talk about the entire molecule having a negative and a positive side. So essentially, if we look at that space-filling model of water, we can say that over here where the hydrogens are is the positive side of the molecule, and over here where there's no hydrogen is the negative side of the molecule. So we can really draw like a line through this molecule and say it has a positive side and a negative side, and that makes it a polar molecule. So water is polar, which means it has what we might call a net dipole. If we add everything together, we have a dipole overall. So that's going to have a lot of consequences in Chapter 11 when we talk about how these molecules can attract each other. Let's look at another example, another molecule. Carbon dioxide. What's the difference between the structure of carbon dioxide and water? Yeah. Yeah, so the carbon's here. We just looked at this structure on the board, but this is our structure of carbon dioxide. And its geometry is linear. It has 180-degree bond angles, just two groups on that central atom. So to spread those two groups out as much as possible, that's going to adopt a linear geometry. All right. So then, are CO bonds polar? Are the bonds in this molecule polar? Well, we have to look at our electronegativities or at the periodic table. We see that carbon and oxygen are about 2 spaces apart, which is significant in the second row. So that is a big difference in electronegativity. And those will be polar bonds for sure. Okay, the difference in electronegativity is about 1. So that will be, these will be polar, which means we can draw dipoles for each of these like that. So now we know that in the structure we have polar bonds, so we have positive and negative sides for each of these. But now we want to know, is the overall molecule polar or not? So what happens when we add those two vectors together? They cancel, yeah. So it says go to the left for this much, and then the other one says go to the right for this much. Since they're equivalent, both CO bonds, that means that we're stuck where we started, which means that if you add these two vectors together, you get nothing. So the net dipole, what happens when you add them together, is 0. So even though carbon dioxide is made of polar bonds, it's not considered a polar molecule. The molecule overall doesn't have a positive and a negative side. It's more like positive in the middle surrounded by negative on the outside. So that's going to be very different behavior. If we look at that space filling model, it's going to look weird on this side because it looks kind of bent, but we know that's not. So if you imagine other molecules encountering this, there's no real way you can draw a line and say, well, this is the negative side and this is the positive side, because the positive side's in the middle, the negative side's in the outside. So that's going to be a different type of interaction. And so what we call carbon dioxide a non-polar molecule. The key to all this is you need to know the shapes of the molecules in order to figure this out. So for instance, I'll give you another example here. Get this all worked out. Let's look at Nh3 ammonia. And let's look at 2 different possible structures for ammonia. It's connected to 3 hydrogens, so one way we might draw that is like this. As a Lewis structure, that's okay. Is that the shape of the molecule? Is that the correct shape of the molecule? Yeah. It's not, because this is actually a group, has 4 electron groups on the central atom. So when they're all spread out, the better way to think about that shape is more of a trigonal pyramidal shape. Now that might seem like that doesn't really matter, but what matters about this is it completely changes the polarity. A nitrogen-hydrogen bond is somewhat polar, going the other direction. So if we add up those 3 vectors in that trigonal planar molecule, we kind of get like the 3 sides of a triangle. So we get this one, plus this one, plus this one, which is 0 net dipole. So they're all going to cancel each other out. If it's pyramidal instead, we can draw the vectors like this. Same bond vectors, because it's the same type of bonds. But they're not going to all cancel each other out now because they're all pointing a little bit up. So the x and y components, if you want to call that x and y, will cancel each other out. but there will still be this kind of Z component that's sticking up. So the net dipole is going to go up like this, which means we're going to have a negative side up here and a positive side up here. So the hydrogens down on the bottom are going to be more like the positive side. The nitrogen up on the top is the negative side. So it has more of a behavior like water because of that pyramidal geometry. If it were planar, it would have zero net dipole. But because it's pyramidal, we have a dipole there. We have to account for that. So that's going to change our prediction for the polarity of the molecule.
So is it like depending on the shape of the molecule, like different shapes can like automatically be like non-polar or something like that?
Right. So actually, any of the, let me see if this is right. So any of the basic shapes, like linear, trigonal planar, tetrahedral, trigonal bipyramidal, octahedral, if they have the same atoms all around, we'll always have a zero net dipole. It's when you start introducing lone pairs, which introduces asymmetry, or when you start switching atoms out. So instead of being like CH4, it's CH3Cl or something like that, where there's going to be some asymmetry there. That's when you'll start changing the polarity. Right. So we need to know the shapes. We need to add the bond vectors, and that's how we determine whether or not the molecules can be polar.
Because like different molecules, like say, like a C and H bond is different than a C and Cl bond, and so like the vectors would be different. We might be stronger in the CCl bond.
Right.
Okay.
Yeah. All right. So we'll get into that more in chapter 11. Let's stop there and take a break, and then because it's a good stopping point. And then the next part will be about orbitals and orbital overlap and hybridization. That should also allow you to complete that molecular geometry worksheet. So yeah, so we'll come back in about 15 minutes and work on that. a lot of what we've been talking about so far falls under the purview of what we call valence bond theory. So the idea of covalent bonding that we've talked about so far, the molecular shapes, the Lewis structures, all that stuff is known as valence bond theory. We don't have to go through like all the specifics of the theory, but the basic idea is what we've just been talking about, that bonds exist because valence electrons come together, the molecules come together so that the valence electrons can be shared in covalent bonds, and that's how molecules get built. From a couple of things that we've seen, like the odd numbered electrons and some other stuff we'll see, this actually isn't a great predictor in some situations. It doesn't work. But for a lot of things it works. So like when you go into organic chemistry, it works pretty well. And so you stick to valence bond theory. But then if you want to look at some more interesting inorganic compounds like these kinds of things, that's not going to work so well anymore. So we're going to look at valence bond theory as we understand it for the simpler molecules that we've been talking about. And then we'll get into molecular orbital theory, which is a more robust theory that can deal with all kinds of other weird stuff. All right. So valence bond theory, we're saying that just valence electrons come together. But we've already kind of caused a couple of problems. I don't know if you've thought about this at all. Let's say we look at a methane molecule. Now we know this structure, right? It's tetrahedral structure. Excuse me. A tetrahedral structure that looks like that. But if we think about it in terms of the orbitals, we would actually get a very different picture. So let's say, all right, valence bonds or covalent bonds come about because electrons are shared within valence orbitals. That's our basic theory. But we know where those electrons are. So if that's the case, then carbon should be, let's see, we're in the 2s, right? So there should be a 2s orbital that has 2 electrons in it. Let's say one over here and one over here. And those those orbitals are being with hydrogen 1s orbitals. To make a covalent bond. That's our valence bond theory. The electrons are getting smushed together, or the orbitals are getting smushed together so the electrons can occupy both valences. So then we're doing that again down here. We've got another hydrogen 1s orbital. But now that takes care of the carbon's 2s orbital, because you can only have 2 electrons in one orbital. So where do the other 2 valence electrons go in carbon? 2 of them are in the s. Where are the other 2? Carbon's got 4 valence electrons, 2 in the s, 2 in the 2s. Where do the other 2 go? Yeah, the p orbital, the 2p. And we spread them out so they're not paired. So that means that there should also be then p orbital here with an electron in it, let's say over there, just so we keep stuff spaced out. That's going to combine with another hydrogen in this theory, right? Another hydrogen 1s. And then we could say there's another p orbital maybe over here. P orbital is going to have these 2 sides, so I've drawn it like that with another hydrogen. So here's the 2p. All right. So there's a problem with that picture in that it doesn't actually show us what we observe in real life. If that's how we were doing our bonding, 2 of the hydrogens would bond with the 1s, or with the 2s, and 2 of them would bond with the 2p. If that were actually happening, then we would expect to see, first of all, a planar structure, because p orbitals are perfectly perpendicular, so you would expect to see like a kind of a plus shape, square planar structure, which we don't see. We see tetrahedral. We would also expect to see lopsided bonds. So we'd have 2 short bonds from the SS interaction, and we'd have 2 long bonds from the SP interaction. That's what this model would give us. And we don't actually see that. Move this over a little bit. So this would be like a planar structure with 2 short bonds and 2 longer bonds. And that is not what we see. That's not the structure that we observe. So we need to change our theory a little bit, or edit it a little bit, to describe how s and p orbitals and their arrangements can still make up a nice tetrahedral structure like we observe. And it's explained by something called hybridization. Hybridization is the idea that instead of having separate s and p orbitals that contain their electrons and bond with these hydrogen atoms, the s and p orbitals combine to form hybrid orbitals. So instead of having an s orbital with its electrons and a p orbitals with their electrons, they all combine. They make these new hybrid orbitals that are part s and part p. Here's an s orbital. Here's a p orbital. And an sp hybrid orbital is really going to look like a combination of the two. It's going to have a big side and a little side, but still kind of have the shape of an sp orbital. So that's known as hybridization. So we can think about this hybridizing in a couple different ways depending on the structure. Let me pull up this picture from the book here. Rather than try to draw this because it's in 3 dimensions, I think it'll make more sense just to look at it. I know it's small, but we just need to really see the shapes. So over on the left, you see that all the valence orbitals for an atom like carbon, or really anything in the p block, you've got an s and 3 p orbitals. And even though carbon only has 4 valence electrons, it still has all those orbitals. They're just unfilled, has those empty orbitals. So if we combine an s orbital with all 3 p orbitals, and you actually can do the math on this and calculate what that would turn out to be, you end up forming 4 equivalent orbitals that point at the corners of a tetrahedron. So you make that exact tetrahedral structure that you're looking for. And you can do this, you can do the math. You can take the x and y and z components of the different orbitals and you can combine them, and that's really what you get. So that ends up being a good model as to what, to be able to explain the bonding in a molecule like methane. Because now we have these orbitals that are pointing in all the correct directions to have 4 hydrogens with a carbon in the middle, if we use those hybrid orbitals. What that looks like electronically, here's our energy. So for carbon, here's the 2s and the 2p. We've got 2 electrons in the 2s, 2 electrons in the 2p. That's our electron configuration. We've got a paramagnetic configuration. When they hybridize, you end up with 4 equivalent, what we call sp3 orbitals. And there's going to be 1 electron in each hybrid orbital. Because the hybrid orbitals are lower in energy than the p orbitals were, this is a net stabilizing factor. So depending on the electron configuration, you may get more or less hybridization. Let's look at those numbers or those names a little bit. There are 3 types of hybrid orbitals. Sp3, well, we'll get to the other ones in a minute, but 3 types of S and P hybrid orbitals. And they indicate how many orbitals are hybridized together. So an Sp3 orbital is the hybridization of all 4 of those S and P valence orbitals all together. And that's where that little 3 comes from. 1 S and 3 Ps all together make these Sp3 orbitals. We can also just hybridize some of the p orbitals. We don't have to hybridize them all. So Sp2 is the hybridization of an S, a P, and another P. And that means that 1 p orbital will be left over. And we'll look at some situations why this happens and when. So in a structure that has Sp2 hybrid orbitals, we expect to see p orbitals that are, 1 p orbital that is unhybridized. It's not combined with the others. It's just on its own. It's just a regular p orbital. And so what would you expect for an Sp hybrid orbital? What is that the hybridization of? Yeah, 1 S and 1 P. So what's left over? Right, 2 p orbitals are left over. So let's look at what that bonding in methane might look like now that we have this new theory. So for methane, if we want to describe the bonding in methane, we're not going to say the 2s electrons bond with the hydrogen 1s and whatever. We're going to talk about the hybrid orbitals. We're going to say our carbon has 4 hybridized sp3 orbitals pointing in those directions of the tetrahedron. This is what a hybrid orbital looks like. That's our sp3 hybrid orbital. So there's going to be one going over there, one going over there, one here, and then one kind of in the back. So there's our 4 sp3 orbitals. Each of those has 1 electron. And those are combining with the hydrogen 1s to make those bonds. 2 electrons per. So each bond is known as, we would say, a sp3s bond, to show that that bond comes from the mixing or the overlap of, sorry, that 3 should be a superscript, not subscript, overlap of an sp3 orbital from the carbon to the hydrogen's s orbital. Okay. If we had something like a carbon-carbon bond, look at a structure like this. This is ethane. So let's say instead of 4 hydrogens on the carbon, we've got 3 hydrogens and then another carbon. We can draw that similarly. Each carbon now will be what we call sp3 hybridized. With its hydrogens. These bonds over here are those same kind of sp3s bonds. So an sp3 orbital mixing with an s orbital. This bond in the middle is two sp3 orbitals mixing together. So it's a bond coming from those two hybrid orbitals. And we can start thinking about larger structures and larger molecules based on this type of geometry being extended bigger and bigger. All right. So the other thing to know about hybridization, before we go on to some more complicated types, is that hybridization and geometry are always connected. And in fact, this is the electron geometry we're talking about. You could say one controls the other, depending on if you think theory comes before experiment or experiment comes before theory. But if you take the case of methane, for instance, it's tetrahedral, right? That's required because of the orientation of the hybrid orbitals. Another way to say that is any tetrahedral molecule, any molecule with tetrahedral type bond angles will always show sp3 hybridization. So they're always connected. And in fact, we can just make a nice table. sp3 orbitals are made up of an s and 3p, which means there's going to be 4 hybrid orbitals. So 4 hybrid orbitals all distributed evenly is always tetrahedral. So that's, if we may make a little picture of this, this is this tetrahedral geometry. sp2 is 3 hybrid orbitals. So if you space out 3 hybrid orbitals, what kind of geometry do you get? Yeah, trigonal planar. So sp2 orbitals are always going to arrange themselves in a trigonal planar way. What about sp? Linear, yeah. So sp, if there's just 2 hybrid orbitals, they're going to be in a linear fashion. So linear molecules, linear electron geometry, meaning just 2 groups, are going to be sp hybridized. We can actually extend this further to include the d orbitals. And let's see if we can just guess this, even though we haven't talked about it. If you had sp3d hybridization, what do you expect the geometry to be? The thing after tetrahedral, yep. Anybody remember what that's called? How many orbitals do you get if you hybridize an s, a 3p's, and a d? 5. So you got to spread out 5 orbitals as much as possible, which gives you this kind of a shape. Yeah, trigonal bipyramidal.
Is there a trigonal pyramidal?
No.
No? All right.
And you could also have sp3d2, where you have 6 of them, and that's going to give you that octahedral shape. So because these go together, it's pretty easy to determine one or the other if you know one or the other. So let me show you how that works. Take out your lab stuff that we were working on a couple days ago with the different geometries, and you filled in half of it. You filled in the shapes already. If I can pull this up also. I need to log in again. So I can write on it. So let's say I don't know. I can't actually write on it because it's like protected or something. But all right, so you've got the first thing filled in. So what's the first one? Somebody tell me. What did you say? Sorry. BH2? Oh, BEH2. Okay. So BEH2, and you drew a Lewis structure. I'm going to assume everybody got it right. Something like that, right? Yeah? Okay. And since we did the first four, you put in that there are two bonded atoms, no lone pairs, the geometry is linear, and the bond angles are 180 degrees. Does that look good? Okay. So now we should be able to fill in that next column, hybridization. What is the hybridization of that beryllium atom if it has two hydrogens connected to it? Sp. How do you know it's Sp? Yeah, because the hybridization always goes with the geometry. So if you've got two electron groups and your electron geometry is linear, that tells you that you have Sp hybridization. Or you could say that backwards, and you could say because it has Sp hybridization, it has to be oriented in a linear way. Same thing, either way. Usually I find most people, it's easier to look at the geometry first and then just say the hybridization that goes with it. All right, so we can always figure out our hybridization just based on the geometry. Let's look at another one from the list here that gives us something else to look at. Let's look at NF3. So NF3, we can draw a Lewis structure like this. Okay. We've got three bonded groups, one lone pair. The molecular geometry is trigonal pyramidal. And the bond angles are somewhat less than 110, right?
This might be what I was talking about when I said, is there a trigonal pyramidal? So that was like that.
Oh, yes. Okay, so yes, that's trigonal pyramidal.
Yeah.
I'm sorry, I was thinking based on bipyramidal, but yes, it's like this. That's called trigonal pyramidal. All right, so we've got that information. So what's the hybridization here? Close. Yeah, remember the hybridization goes with the electron groups. So we've got 4 electron groups in this molecule, which means we need Sp3 hybridization. In a molecule like this, that lone pair will take up one of the Sp3 orbitals. So we can think of that structure as having the nitrogen here, having our 4 hybrid orbitals connected to the F, and then having that lone pair in that 4th hybrid orbital. And that gives us that trigonal pyramidal geometry that we know we have here, those bond angles. So these angles here between these orbitals are going to be just under 110. So that's this idea of valence bond theory, that the bonds come from the valence orbitals or the valence electrons hybridizing in these, or being in these hybrid orbitals and then coming together to form covalent bonds. The last part of this then is thinking about what happens with these leftover orbitals. So what happens when we have something like sp2 hybridization with leftover orbitals? What's that leftover orbital going to do? Let's use our beryllium first as an example. If we draw a representation of what's happening in that beryllium dihydride molecule, we've got beryllium here, and we said here that it's going to do sp hybridization. So how many total hybrid orbitals do we have? 2. Sp makes, if you take an S and a P, you put them together, you make 2 hybrid orbitals. So we've got 2 hybrid orbitals, and they're going to be spaced apart from each other in a linear fashion. Sometimes I forget to draw the little extra part of the hybrid orbitals. So there's our 2 sp hybrid orbitals. And those are going to be bonding with hydrogen s orbitals. So that's the basic picture of our bonding. We've got hybridization, we've got the s orbitals. But we've left something out. So what orbitals are left over in that hybridization scheme? If you hybridize an s and a p, what's left over? Yeah, there's 2 p's that we haven't dealt with that are just there. And so in this molecule, they're just there. Nothing's happening to them. We've got one here. And then we've got one perpendicular, which means it's kind of going out and coming back. Like this. So those are those leftover p orbitals. They're just hanging out on that central atom, not really doing anything. But that doesn't have to be the case. Those p orbitals can participate in bonding. And they participate in a little bit different way. So let's look at an example of that. Let's look at formaldehyde, which is CH2O. So we can draw a Lewis structure for this. We've done this one before. Looks like that. What's the shape of that molecule? What's the shape on the central atom? How many groups are on the central atom?
4.
Close. 3.
Oh.
The double bond still counts as 1 group, even though it's a double bond. So we got 3 groups, which means what kind of geometry is that? It's trigonal planar. Okay. So 3 groups, trigonal planar. And what's the hybridization on the carbon then? sp2. Yeah, sp2 hybridization on that central carbon. So that means we've got 3 hybrid orbitals that are pointing toward those other atoms. And then there's this leftover p orbital. We'll get to that in a second. Let's just focus on what's happening with that p orbital. So I'm going to draw this like this. Kind of like sideways, like we're looking at its side there. You can imagine this kind of coming out at you, and this one going back. So we tip that molecule on its side. It's a flat plane, and all those connections are being made by those hybrid orbitals. But there's this leftover p orbital on the carbon, and that leftover p orbital is sticking straight up like this. And so the way that that can bond, because in carbon it's actually going to have an electron in there after the hybridization, is it can bond with a p orbital on the oxygen. Oxygen is going to have a p orbital that also has an electron and is sticking up the same way. But because of the geometry, those two can't like mix in the same way that the hybrid orbitals do. They can't just kind of become covalent like this. So they mix parallel and end up kind of bonding like this. And that's a single bond, even though it has 2 pieces. And it's given the designation of pi, the letter pi, as in it comes from the p orbitals. These other types of bonds that we've been dealing with, like right here, are called sigma bonds. So when two orbitals just like smush right up against each other, that's called a sigma bond. When parallel orbitals, parallel p orbitals, d orbitals can do it to some extent too, but we're not really going to get into that. When parallel p orbitals bond without smushing into each other and on two sides of the molecule, that's called a pi bond. So if we were to be more specific about this molecule, here's our hybrid orbitals from the carbon. And that's actually going to be mixing with an oxygen orbital, an oxygen p orbital right here. So you have a sigma bond here and a pi bond around it coming from the p orbitals. So a double bond is always made up of a sigma bond and a pi bond. Even though the pi bond looks like it has two pieces to it, that's still considered one bond. It's just two electrons being shared, just in a different geometry.
What a triple bond have?
So let's look at a triple bond. We can look at C2H2, which is acetylene. The Lewis structure looks like this. In this case, each of those carbons can be considered as having two groups on them. So that's Sp hybridization on each one. Do we have a picture here? Yeah. So this double bond, or this triple bond in the middle, is one sigma bond and two pi bonds. And rather than try to draw this, which is going to get super messy, let me copy the picture from the book. So that's what it looks like. We'll go through it, what that means. So you still have your hybrid orbitals in purple here. So let's just look at each carbon individually. Here's your carbon with two hybrid orbitals in a linear geometry, one on either side. One of those hybrid orbitals is bonding with the hydrogen. The other is bonding with the other carbon. And the same thing's happening on this side. These big red blobs indicate the two different pi bonds. One that's going in this way, the same way as the previous structure that we made right here. And the other one is perpendicular to that, coming out at us and going back. So you've got a sigma bond here, the sp-sp sigma bond. Then you've got two different pi bonds from p to p. So unhybridized p orbitals bonding together makes pi bonds. So if we go back to our chart from lab, let's finish filling these up. In that first BeH2 molecule, how many sigma bonds are there? Overall in the molecule? Two, yeah. Single bonds are always sigma bonds. Only multiple bonds can have pi bonds. So those sigma bonds are just two of them. But what about in the structure below, the NF3? How many sigma bonds there? Three, yeah. Do either of those structures have pi bonds? They don't, not as we've drawn them. If they had double bonds or triple bonds, then we would count some pi bonds. So no pi bonds in here. And then I'll let you decide if they're polar or non-polar based on what we did earlier today. So you can add up the bond vectors and do that. So this is why when we draw Lewis structures with double and triple bonds, we kind of have to be careful whether or not that's really meaningful. because in this valence bond theory, this overlap theory, we have to ask ourselves, okay, well, are those p orbitals actually bonding and sharing electrons or not? And that's where it comes up in some of these structures like SO, where we often draw SO double bonds in our Lewis structures to minimize formal charge. But in reality, the orbitals between S and O wouldn't line up really well enough to make a good pi bond. So it's unclear as to whether that would really truly be a double bond or a pi bond or not. So that's where some of the Lewis theory can break down a little bit. Okay, so that's the basics of hybridization. The last bit of chapter 10 is molecular orbital theory. I'm inclined to save that just because this has already been kind of a lot, and we can work on that another time, I think. So with our remaining hour or so, I want to make sure that we have plenty of time to get back to some of the material for the exam, for practice, and for questions. So let's stop there. That should give you enough information to complete the lab, and once you get to do the homework in chapter 10 and get ready for the quiz on Thursday.
Are we turning in this lab?
Yeah, it's part of the, it's technically part of the organic compound one, so it'll be due, no, the week after.
Oh, next one.
Yeah. Okay, so what do you want to look at more? You want to do gas stuff? You want to look at quantum stuff, electrons, Lewis structures? What would be the best use of time here?
Like 7 and 8, probably. For me.
Start with 7 and 8? Yeah.
Is this recording for
I think so. Let's check. Yeah.
And I'll subject to like 7 and 8. I think that's
All right, let's start there.
Can we also do a try to find a problem of the like gases over water?
Oh yeah, okay. Let's start there. That's a good place to start. So one way to check yourself and see if you're ready for this exam is to just randomly go through the chapter, just put your finger on a problem, and then see if you can do it and get it right. So we're going to try to do that now, where I'm just going to grab a problem and we'll take a look at it and see if you can do it. So if you're following along in the book, this is number 68. I think this was in the homework too.
Yeah, this is the homework. I could not understand how to do it.
All right, the air in the bicycle tire is bubbled through water and collected at 25 degrees C. The total volume of gas collected is 5.45 liters, blah, blah, blah. How many moles of gas were in the bicycle tire? All right, so there's no surprise here because we were looking for a problem like this, but on the exam it'll all be mixed up. So the trick is to look for something like a phrase like that that says bubbled through water. And that tells you you need to correct for that vapor pressure of water. So as this problem is written right here, we don't have enough information because we don't know the vapor pressure of water at 25 degrees C. We have to look that up. So that's something you'd have to be given. There's no magic way of just figuring that out. So let's look it up. Okay, so the pressure, vapor pressure of water at 25 degrees C is 23.78 torr. Okay, how do we use that information? So we know we somehow have to correct for this. How?
The overall pressure from the pressure of H2O.
Yeah, well, yeah, the opposite of that. But right, so what we're saying here is, if you think about what's actually going on, that can help make sure it's clear. You've got some volume of gas in a container that's creating a particular pressure, 745. But there's water there also. So that means that part of that pressure is coming from the water, and the rest of it is coming from the stuff that we care about, whatever we're actually trying to measure. So we have to subtract out the part from the water because we don't want that in with our measurement. So that's how we would start this. So we'd go, the pressure of just the air is the total pressure, 745, minus the amount from the water. So that's what makes a problem like this special, is just that we have to remember to subtract the water. The rest of the problem is just a standard ideal gas problem. Yeah. Yeah, you'd have to be given that. Yeah. It may not be right in the problem. I may just put like a table of them on the back or something. But yeah, that would have to be given. So the rest of it is you're solving for moles of gas, so that's just a standard gas law problem. You've got volume, you've got temperature. We just need to make sure that we take the air, just the pressure of the air, as our P, not the total pressure. So we subtract the water first, then solve whatever ideal gas stuff we need to solve. All right, does that make sense? Yeah. Okay, yeah.
All of the gas equations,
What do you mean all of the gas equations? So you should know the ideal gas law and the various other laws that we talked about, like Boyle's law, Charles' law, all that kind of stuff. You don't need to know all the equations at the end of the chapter, like the root mean square velocity, or the effusion rate, or the like kinetic energy, any of that kind of stuff from the last half of the chapter. You don't need to memorize. The what's the other one? The real gases.
So like the finishing problem,
Yeah.
We have to like convert Celsius into Kelvin and then Torr back into
Atmospheres.
Okay. Yeah,
Yep.
So would you be able to tell? Okay, so temperature should always be in
Kelvin, right?
Kelvin.
So we got to go 25 degrees C is 298 K, and then that 721 torr divided by 760. 0.949 atmospheres, and then plug it in. That's all for it.
And then volume, is that in liters or is that
Liters, 5.45 liters.
200?
Right. And if you're ever questioning your units, check R, because constants are always given on the exam. So like if I gave you R, it would say R equals 0.0821 liter atmospheres per mole Kelvin. The constants are the ones that cancel out all the units, so you can check the constant to make sure you have all the right units on everything else. Yeah. Because also I'll use the regular constants that are given on the final exam. There's another R that's given also that is in different units. So just make sure you're using the right one based on the units you have. All right, you want to stick with gases or jump into other stuff? Jump into other stuff? All right. We can do that. Yep. All right, let's take a look at so here's an interesting hydrogen atom question. I think this was on the lab, the flame test lab. I don't see it. I know it's in the book here somewhere, but I don't remember where it is. So given the Bohr equation, I don't see where that one, where that is. All right, so we know that the Bohr equation is going to be, I'll just give you the number here, minus 2.18 times 10 to the minus 18th joules. So that's the equation. I'm going to ask this a little bit differently. What is the energy required to ionize a hydrogen atom? So normally a question about this kind of thing would say, you know, what's the difference in these two energy levels, or how much energy does it take to promote this or whatever? I ask, what is the energy required to ionize a hydrogen atom? So what does that mean? First of all, what does it mean to ionize a hydrogen atom?
To remove the electron?
To remove the electron. So thinking in terms of energy levels, what does it mean to ionize an electron?
Get through the first ionization.
Yeah, so what's happening with the electron then? It's leaving. What energy level is it being promoted to? Infinity, right. So you're saying, what would happen, how much energy do you need to not just promote the electron from level 1 to level 2, or level 1 to level 5, or level 1 to level 10, but from level 1 so high that it actually leaves the atom?
Or infinity.
Which would be infinity, like infinity levels.
That's like not possible.
It is possible. It is possible. Because you can ionize a hydrogen atom, right? We know that can happen.
I know. It's like
All right.
Not right.
So how does that apply to this question? How can you substitute in for NF and NI, thinking about the ionization of the electron?
You can plug in affinity to F,
Mm-hmm.
1 over infinity by 0.
Yeah, so that's really,
So then you just go
that's what we're saying here. So we know the initial level is 1 because it's starting at the ground state. And we are promoting it to infinity. Okay. If you don't like infinity because it's too weird, just think of it as like a million or something, some really, really big number. So if you had some really, really big number on the bottom of that fraction, and then you square it, that fraction becomes essentially 0. Right? The bigger the denominator becomes, the smaller the overall fraction becomes. So this becomes, we could say, essentially 0. And
Does it actually become 0, or does it become such a small number that you can't even quantify it?
Well, if the bottom, I don't know what the actual math term of that is, if it's like indeterminate or undefined or something like that, but
it's basically.
I think the better way to describe it is the limit as that goes to infinity is 0.
Okay.
Yeah.
Is the way that we could say it.
It's because it's such a large, like you can't, it's not even,
Yeah.
it's infinity, so
Yeah.
1 of infinity would be virtually nothing.
Yeah, and I mean, so it's not technically, it's not purely, it's not really infinity, right? Because we know that it actually happens. And if it were actually going to infinity, it would never actually leave, because infinity is infinite. So
It's not really.
I don't know how to like describe it in a rigorous math way, but we can just say like, if we imagine that as some huge number, that fraction becomes 0, or essentially 0. So the other one becomes -1. So that means that the ionization energy for 1 atom of hydrogen should be -2.18 times 10 to the minus 18th joules. Or not negative, it should be positive. That's the energy that it would require to ionize that electron, to promote it to such a high energy level that it actually leaves. And since that's per atom, if you multiply that number by Avogadro's number, you should get something approaching the ionization energy of hydrogen in kilojoules per mole, if you convert your to kilojoules. Yeah.
You flip the, oh no.
All right. So what are some other things that you should know about this chapter? Let's look at this one. This was like from the quiz today, so we kind of reviewed that anyway. We can just do this one, just looking at it here. So 62. Which combinations of N and L represent real orbitals and which do not exist? So of those 4, which are real and which do not exist? Does anybody find one that does not exist? D doesn't exist? How do we know D doesn't exist?
Because D orbitals are trying to build the third row.
Okay, so how could we say that in terms of quantum numbers? Yeah. Okay, so getting closer. How do we say that in terms of quantum numbers? Talk about N and L and that stuff. You're all saying correct things. I just want to also be able to say it in this other language.
Unless I would like N to L, like N like L to N minus 1. But
Yeah, you're on the right track. So we could say that the maximum value that L can take is N minus 1. If N is 2, that means that the maximum L is 1. But D represents an L of 2. So that violates that rule. But, I mean, however you came to that conclusion is right. So are the other ones all possible then? Are those all real orbitals? Yes, they are. You can have P's start in the N equals 2 because then P equals 1, or then L equals 1, sorry, and the S's are in all additions. All right, let's take a look at some of the Yes, I was going to jump over to chapter 8 here. Let's look at some ion electron configurations, because that wasn't on the quiz. All right, can we do an electron configuration for each of these ions? What's the electron configuration for each? See if you can write it. See if you can write each one. Remember, as you're studying this weekend, be honest with yourself. It's easy to look at a problem and go, yeah, I think I know how to do that. But if you actually force yourself to do it and then check your answer and see if it's right, that'll give you the real sense as to whether or not you can do this on the exam.
If like Cl minus becomes a noble gas, and can we just say the noble gas comes in the parentheses, and that's all we need?
Yep, it's generally customary for something like that to show it as still the previous noble gas,
Yeah,
but then fill it up. But it's technically correct to just say that it's the argon
yeah, that's
configuration.
That's what okay, D is, no, never mind. I thought D would be weird, but it isn't actually. Right. No.
All right, got some configurations? Okay, let's look at them. So chlorine, as we were talking about, chloride ion would be one to the right of chlorine, which would be argon. The more conventional way to write this would be to say 3s2, 3p6 to really emphasize that it's gotten that. But you could also just call this the argon configuration. Okay. Same thing with phosphorus, 3 minus, it's going to be the same. Same thing with potassium +1. All three of those are isoelectronic. They have the same electron configuration. They all have 18 electrons. Molybdenum 3 plus, so molybdenum is 42. So with these, you know, if you've got practice and it's not a big deal for you, then go for it. But it's usually a good idea to write the electron configuration first and then think about where they would be taken out of. So we would write this as 5s2, 3d4, and then we'd recognize that that's about halfway. Whoops. So that would instead likely be 5s1, 3d5. Sorry, 4d5. That's for neutral molybdenum. So then we take 3 electrons away. That's going to be the S and then the D. So we always remove the S first. So the 3 plus should be
Why do we remove the S first?
because it's higher in energy.
So the S's are higher, 5S is higher energy than 4D?
Right.
Okay.
Yeah. They're very close in energy, but because they're the outermost, those will come out first. Just slightly, but it's a little trickier than that, as we talked about, because what we're saying is the D fills first, but then some of those end up getting pushed up to the S once they're in the atom. Yeah. Yeah.
I just don't quite understand why it goes 5s1, 45.
Oh, at that position in the periodic table, 6b or 6, whatever you want to call that, instead of having 5s2, 4d4 or 4s2, 3d4, one of the electrons stays in the D rather than being bumped up to the S so that it can have a half full shell. You can think about it as like pairing energies. So if it's 4d, sorry, I'm going to get a little confused. If it were 5s2, 4d4, you'd have paired electrons in the S and all unpaired in the D. But if one of those electrons stays in the D, then they're all unpaired. And so that's usually what happens instead.
It's an exception like copper is.
Right. That position in the column group 6 and also group 11 tend to have that exception.
So you want to fill up first. You want to have an electron in each orbital
Before you pair. But that doesn't hold for the other one, so that's not like a big general rule. It's just at that position.
So it'd just be like 6b.
And 11 or 1b. All right, so same thing with vanadium then. So that one's going to be our neutral vanadium is argon 4s2, 3d3. And so this is a tricky question because you see that it's 3 plus, you see that it's 3d3, so it's really tempting to just pull out those 3d3 and leave it as argon 4s2. But we have to remember that the s electrons the 4s are the outermost electrons, so those are the ones that come out first. So vanadium 3 plus is going to be argon 3d2. So those 2 are going to come out of the S, and then 1 comes out of the D. Did you say to leave it 130?
No.
Okay. Just want to make sure. All right, so that's electron configurations. Let's look at this one. Oops, yeah. 57. We're Which experience a greater effective nuclear charge? The valence electrons in beryllium or the valence electrons in nitrogen? Why? Which one has the greater effective nuclear charge? Why?
Because as you go from left to right on the periodic table, then doesn't the charge of the nucleus go up, so it holds on to the electrons more tightly?
Yeah, right. So you've got, when you have more protons, you have a greater effective nuclear charge, since all of the electrons are in the same n level, the same energy level. So in between beryllium and nitrogen, you've added 3 electrons and you've added 3 protons, but the 3 electrons are all in the same spot. So they're not really shielding each other that much. So you just have a greater effective nuclear charge from those more protons. So nitrogen has the greater effective nuclear charge. All right, let's look at, I'm just going to give part of this next question. Is gold 1 paramagnetic or diamagnetic? And write the electron configuration. Let's see. Just see that. All right, got electron configuration? So first of all, that first question should be relatively easy without even doing the electron configuration. How could you, do you remember what those definitions are? Paramagnetic versus diamagnetic?
Paramagnetic is unpaired electrons.
Yeah, paramagnetic has unpaired electrons, diamagnetic doesn't. So what do most atoms fall into? Which category? Yeah, para, because only the ones with the full shells can be diamagnetic. So just looking at gold's position in the periodic table, the fact that it's just a 1+ ion, it's unlikely that it can be diamagnetic. So it's probably paramagnetic. We can write the electron configuration, look where those electrons are just to be sure. So that would be, start with xenon. Then we jump down and go 6s2. After that is the lanthanides, so that's 4f14. Then we get into the d electrons, and we've got 9 d electrons. So 5d9. That's for just regular old neutral gold. If we remove one electron, we're going to take one out of the 6s. And realistically, we're probably going to take both of them out of the 6s so that this can be 5d10, because we know that full shells are a good thing. So that changes our initial guess, right? Because now we can see, oh yeah, that probably has a full shell, so that's probably diamagnetic. So just looking at it, seeing that it's kind of in the middle, I would have guessed paramagnetic, but when we actually look at the electron configuration, we find that it's diamagnetic because everything's full. Okay. Jump into chapter 9. A couple things chapter 9 that weren't on the quiz. Something like this. Number 45, the lattice energy, let me copy it over, of cesium fluoride is -744, whereas that of barium oxide is way bigger. Explain this large difference in lattice energy. You want to give that a try? You got two different ionic compounds, seem relatively similar. What's going to be the difference? Why such a huge difference in lattice energy? This is 9. What causes that big difference? What are the two things that affect lattice energy? There's two factors that make a big difference in lattice energy. Yeah. Charge and size. So which one is the effect here? It's going to be charge, because cesium and barium are around the same size. Oxygen and fluorine are around the same size. There's a little difference because of the size trend, but we know that, like, just ionic-wise, that's not going to be a huge difference. Or I'm sorry, atomic radius-wise, that's not going to be a huge difference. Of course, these are ions. So the charge ends up being the big difference. Cesium, oops. Cesium is +1, fluorine's fluoride's -1, barium's +2, oxide's -2. And we know that's a really, really big effect, that those more highly charged ions can attract each other more strongly. And so that should lead to a larger lattice energy. All right. What about this one? Another thing we didn't really look at on the quiz today was bond strength and bond length. Let's look at these two nitrogen-containing compounds. The question is, which one has the stronger nitrogen-nitrogen bond and which one has the shorter nitrogen-nitrogen bond? How could you figure that out? Or what would be a good first step here? What could you do first to try to figure out the strength or the length of that bond? Just stare at the problem until it magically appears. Yeah.
I'd say, just from looking at it, say, the H and H would have stronger nitrogen bond.
Why?
Because there are less positive charges there.
Yeah, but that issue of polarity doesn't necessarily translate to strength. Like you're saying that it's more polar, so that it would be stronger, or less polar, so that it would be stronger. That doesn't necessarily work like that. There's plenty of polar bonds that are extremely strong. It's good thinking, but what could you do to maybe see if something pops out at you? Yeah, draw the Lewis structures, because maybe when you draw those structures, it'll become more apparent, even if it's not just looking at it right here. So see if you can draw those Lewis structures. Do you see it? All right, so what did you find looking at the Lewis structures of these two? Anything interesting? Anything different about the two? Yeah, go ahead.
The first one has a double bond and nitrogens.
It does? First one?
Right?
Is that what you got?
I put a double bond.
Oh, okay. That would give you too many electrons on nitrogen then, right? Because you got to have these two pairs. Because the total electrons here are 14. So we need 2, 4, 6, 8, 10, 12, 14. So if you took one of these and made it a double bond, then this nitrogen would have too many electrons around it. Because then it would have 2, 4, 6, 8, 10 electrons. So that doesn't quite work. The second one does. Like that. The second one needs those double bonds. So then which one has the stronger nitrogen-nitrogen bond? The second one. And what about the shorter nitrogen-nitrogen bond? Same. It's actually the same. Length correlates with strength, with some exceptions. But when we're talking about multiple bonds, that certainly holds. So multiple bonds are always shorter than their single bonds. Yeah. Stronger and shorter. All right, what else? Anything else interesting? All right, so for Monday, we got the exam, so please be ready. It'll be some multiple choice, some other stuff. Be ready to solve gas type problems. Be ready to draw Lewis structures. Be ready to give quantum numbers and explain trends in the periodic table. If you don't feel like that, you can withdraw from the class before Sunday. But if not, I will see you Tuesday or Monday.
And then we won't be given like the names of the, elements.
Yeah, I think you will. So we'll still give you. We'll use the same cards. It'll just be for the final that you don't get them. Yeah.
So what will the grades actually find?
You mean for everything up so far?
Everything up to the-
Everything up to the exam should be done within the next couple of days. Whenever I finish getting to the lab reports. Oh, and the homework, there's a homework due tomorrow. So I'll add that in after that's due. I think 7 and 8 are due tomorrow. And 10 will be due the next week. And 9 is just for practice.